Alrighty, in today's video, I'm going to show you everything you need to know and things you probably, almost positively don't know about balancing. But first, let me answer last week's question about Cletus's rollerized thrust bearing and align hone. So the question, one of the very first questions we had in here was a really good question. And it's from user RS2UE3RS7Y. FYI, need to get a new username, something a little easier for me to stay. Okay, so the question, when line honing, is there a limit to how many times a block and caps can be honed? And if it's multiple times, is there a threshold or change needed in bearing selection, i.e. does the bearing shell need to at some point become thicker in order to compensate for the honing? And what do the numbers mean on the shell? Okay, what the numbers mean on the shell is dependent upon the manufacturer, so I'm not going to answer that one, because they're all over the place. But it is a good question on line hone. So Cletus's brand new block started small because they had only bored it, they hadn't honed it to size. It's very, very hard to bore to absolute perfect size. That's why everybody, in general, hones to the very final tenth of a thousandths, okay? So it started out small and we honed its size. Now that's an easy one. Now what your question is if the block is a little bit big and then you machine the cap down, let me show you on this billet aluminum Pontiac. Now this is the same. Every engine, regardless, when it gets line bored or line honed, doesn't matter if it's a Formula One engine, a Winston Cup engine, Pro Stock engine, Cletus's engine, your mom's Toyota Camry, don't freaking matter. This is exactly the way it's always done, okay? I don't need that. So we'll just run these down. So your question was, this is just a for instance, all right? In fact, it's not even right cap. Hold on, there we go. That's fine. When honing this hole, after it gets real big, well, we cut this surface right here and we make this hole smaller. But what it doesn't do is we make the hole smaller this way. So imagine it does this, okay? Imagine it's right here. We cut the cap and it makes it like this. Okay, that's exactly what it's doing. Let me grab this cap, it's easier to look at. It starts up here. It's a round hole. We make it unround like that. All right. Now, what happens is when you make that hole unround like that, we can make it back being round, but it does take material out of this block. And you know what it ends up doing? It does end up making this center line closer to the camshaft center line. It does actually move the crank down in the block. So, how do you correct that? You don't. You can't. What we can do is in like a top fuel car, or there's some real elaborate guys out there that actually will resaddle this. They will machine this out, like cut a 1/4 inch of material all the way out of here, put a new saddle plate in it, and then remachine it back on center. That's really extensive. Most of the time, we're only talking thousandths at a time. Okay, we're not talking like a 1/4 inch or a 1/2 inch or 1/8 inch or a 1/16 of an inch. 1/16 of an inch is 62 thousandths. We're not talking a 32nd of an inch. That's 30 thousandths. We're basically maybe talking about like a 64 thousandths of an inch, which is 6 thousandths. So somebody's gonna correct me because I'm just doing the math off the top of my head. But very, very minimal. So normally what would actually happen is if you had to machine too much material here in the block, because for some reason we had to go down too much and made that hole unround here, well, it's going to take equal amount here, equal amount there, therein dropping the crankshaft. If we do that too much, what we ended up having to do is you would get a shorter timing chain, which they do make. They make shorter timing chains. And on like a SMX or anything with a gear drive, they'll make the idler gear smaller because you either make the idler gear smaller or you make the bottom gear smaller, because the bottom gear of the crankshaft has actually gone down or up, has gotten closer to the camshaft. So the two gears, center of the gear here, center of the gear here, has gotten a little bit closer. So one gear has to be made smaller. So I can buy a 10,000 smaller gear, which fits a line hole block. You see that? Cody's over there going, dang, I didn't know that.
Yeah, I didn't know that.
Yes, you can. So this crankshaft drops down. So we can fix it, but you're correct. There is a certain limit you just can't do, but most of the time, most engines don't get hurt this in the main saddle very often. It's pretty rare. And if they get hurt too bad, we don't even bother. They just scrap it. That's one thing that we do scrap blocks for, is if it gets really destroyed in here. All right. Then, before we get to the balance job, so I thought you might find that's a really good question. Contact me. I'm going to send you a shirt. That'd be cool. Then, the next question is a good one too. Not getting a shirt for this, but so I'm not going to say your name, but when honing a cylinder is the ideal angle for the hone to be at in relation to the horizontal, and so what determines in the high angle constant for the piston based internal combustion engine regardless of bore stroke, blah blah blah. And he had a couple other questions. Funny you should ask. That's in the next video on Thursday, which is Cletus's block in the king of all hones right here. I'm going to do a real detailed how and what and why you actually hone. How do you hone the block? What is the crosshatch? How deep is the crosshatch? What is your RK, PK, VK? What are those numbers supposed to be? What do they mean? What do they do? What are you talking about? I have no freaking idea. It applies to your 350 Chevy, your 289 Ford, your 302 Ford, your NHA Pro stock, your Formula One. Honing is like critical, super important. And I'm going to talk to you about all that in Cletus's next video on Thursday. But for right now, let's go over here and I'm going to show you stuff on this balancer that you're going to go, oh, I didn't know that. That's weird. Let's get at it. I got a lot of questions on balancing, and I have something that'll make you'll think it's crazy to go. But I thought, let's show you, since Kyle's got to balance his 302 crank, so a 302 Ford crank. Now, first thing I want to say is that this crankshaft is probably, that's a stock crankshaft. This crankshaft is maybe worth $100, okay? My SMX crankshaft or any other crankshaft, doesn't matter what it's out of, how much horsepower it makes, anything, it balances exactly the same. The process is exactly the same. So if you see me balancing or doing almost anything, whether it's installing camshaft, whether it's checking bearing clearances, whether it's torquing something, whether it's doing valve lash, every single thing I show you on a big horsepower engine is exactly the same principle, might just be different numbers, on your average 302 Ford or your average 350 Chevy or your average LS or whatever it may be. It's exactly the same, right?
That's right.
It is right. Every principle is exactly the same. So let's get to it. So me showing you this is, and I'll talk to you, is exactly the same way we balance the SMX crank, SML crank, or any kind of really big high dollar stuff. It's exactly the same thing. So first things first, crankshaft goes in the machine. Kyle's already got it up here. The first thing you have to do is you have to build a bob weight. Now, this is a bob weight. What this bob weight does is it simulates the piston and connecting rod, everything that's rotating and going up and down on the crankshaft, right? So Kyle is, and we have to separate it because there is rotating weight. So everything that rotates is going around, okay? Reciprocating weight goes up and down. So this end of the connecting rod, the piston, the ring, the pin, everything that's up here is reciprocating weight. Everything that's down here is rotating weight. So first thing we got to do is we got to measure it up. Now, Kyle's got some aftermarket rods and he's got stock pistons. So we're still going to make sure that everything weighs the same. You would grind if you wanted, if this rod weighed, well, he doesn't have another one over here. pretend this was the same rod. This up here is a actual balancing pad from the factory, okay? That right there is an actual balancing pad from the factory. If you were, or what you would do is, in order to make everything weigh the same, you would find the lightest one, and then you would make all the rest of them the same weight as the lightest one by grinding material right here and grinding material right there. That's how you would balance and get every rod to weigh the same. Because it needs to be measured, we have to measure the small end and the big end separately. So you got to have this special little stand fixture right here. And so that rod end weighs 167.7 grams. Alrighty. Now, this is the rod he's replacing with this new rod. Now, we're not going to make this rod match the old one, but we want all the new rods to match each other. Okay? So this weighs 140. Oh, that rod is just lighter all over the place, isn't it?
Yeah, no, I weighed them earlier. Just the difference, just in the straight up weight, like
Yeah.
total.
Total weight, 512.
513.
563.
Yeah.
Now, what you'll find out is, it's pretty interesting, and it makes perfect sense. 140, and then when we weigh the big end of the rod, it actually, both the numbers added together and equals the total weight, which is logical, right? Okay, so you make the rod ends weigh the same, you make the big end weigh the same, you get that number, enter it into your computer. All right, now you're gonna weigh your piston. Now, where do you balance a piston pin at? Don't touch it. Don't think about it. Don't do anything other than weigh it. If you have piston pins, that is a machined part, almost astronomically hard for it to weigh any different. And there's no place that you can grind or do anything different with it. Okay, but the piston, if you're all gung ho, you can weigh your piston there. That weighs 568. You got your other pistons over here.
They're all the same.
Okay, you weighed them and they're all the same.
No. I thought you were asking if it had other, like, aftermarket business.
No. So this would be about the same thing. So typically, this is a pad that you would do a little bit of grinding on. Do not get all gung-ho and remove massive amounts of material off of these. They should be within a couple of grams of each other anyways, okay? And there's maybe some other little spots you could maybe hit if you're trying to remove material, but try to take as minimal amount of material out as possible. And there's usually a little pad or a little spot you can do it in. In an aftermarket race piston, this is usually flatter, and you would grind like off the edge. Usually I'd grind here and grind here in an aftermarket piston. Now, in really big high-end pistons, when you buy a set of really expensive pistons from us that are really, really nice, they're the same. Don't touch them. Just weigh one, don't touch them, okay? Because they're fully machined. All right, so weigh that one. Or here, we'll set 0, right? So we'll see how much different these are from each other.
1.8.
Right. 1.8 grams. Okay. Now, let's pretend Kyle's going to go through and make these all weigh the same, so we're not going to waste your time watching that, but he'll, kind of grind them and do something there to make them all weigh the same. So let's pretend everything is correct weight. So we have the piston weight. We enter in that number. All right, up in our screen, piston. Then we would enter our piston pin. If we have any locks or pin buttons or anything, you would put it in there. And then our rings, okay? So we enter in all of those numbers into our bob weight calculator. So we have entered everything in the reciprocating. So the small end of the rod, piston, pin, rings, locks, anything else. Then on the rotating side, we measure the big end of the rod bearings. All right, enter that all in. Make everything weigh the same. That's all cool. All right, and enter all that information in. All right, now, so everything's weighed the same. Now we're going to generate what our bob weight number is. Now this is all just showing you the numbers, okay? So don't get hung up. Kyle hasn't gone through and done all this yet. We're just showing you how to actually do it and haven't done it yet. So bob weight, if nothing else changes, would be 1734. All right. Now, I'm going to show you some stuff later that is going to be crazy. All right. So hang on. So after you're going to learn something, probably that 98% of every race car guy, engine guy, possible engine guy doesn't even know about balancing, and give you something to really think about. All right. So now this is a external balance crank, and Kyle's going to keep it that way, right?
Yeah.
So when it's external balanced, that means that the dampener and the flywheel or flex plate have a weight on them. So there's actually a, loosely paraphrased, we'll show it here in a minute if you want to grab that balancer and your flex plate, has a weight that's going around out here, and it is a counterweight that is part of the way Ford and Chevrolet and their in their 400 cranks or big block Chevrolet cranks are externally balanced. Okay, so it's not just Ford. A lot of other companies do the exact same thing from the factory. That is a pad of material, and if this pad of material right here, this being an externally balanced crank, if you don't have the right flywheel, or if you get an internal one that doesn't have this big pad of material there, when you spin this crankshaft up, it will throw the freaking crankshaft on the ground. It is scary. Now, when we spin this thing, you'll see it's pretty scary anyways. Okay. And there's a reason why. I'll explain why, as we're spinning this, why you don't spin this at like 9,000 RPM. Okay. Why it's fairly scary to even get them up to 1,000 RPM, because stuff is flying off of it like crazy. Now here's your dampener, and you notice this is weight removed, or you think of it as this is weight added. Okay, so this is externally balanced. Those have to be on the crankshaft in order to balance it. Now, if you're going to internally balance a crankshaft, that means there's no weight here, there's zero balance. The dampener will be zero balanced, the flywheel will be zero balanced, and you would just balance the crankshaft. You can put those on, but don't touch them, don't mess with them, only do the crankshaft. That way, if you ever had a problem, one of the good things about internally balanced stuff is you can change it without having any effect on the crankshaft. It's zero balanced. They're zero. Okay, so you're going to put that stuff on after we build the bob weight, simulating everything that we have here, and spin this thing up. So let's let Kyle build this bob weight for him. He's going to actually go through and set the measure everything up and make them all weigh the same, so we're not going to bother showing you that, but he's going to build the bob weight. Then after he's got everything the correct weights, and put this on, we'll put the flywheel on, the dampener on, and we're going to spin this thing up, and then I'll talk to you about the RPM and stuff. Generally, we do it at 500 RPM. Can you spin it faster? Probably. Is it dangerous? Darn right it is. You'll see why.
All right, so now we're building our bob weights. We see we've got one bob weight sitting up here. I've just got it roughed in basically. And we have all these different weights, as you can see back here, that we can change the bob weight with. We've got them all the way down to these, which weigh like, I think these are like 0.5 gram or something like that. And we go all the way up to these ones, these heavy guys. So we're just mixing these back and forth evenly on each side to try and achieve our bob weight, which is 1734.2. 1732. 1734.1. So there we go. Now that we've got the first one built, it'll make it easier for building the rest of them to just look at this one and then weigh them before I put them on the crank.
Now, while Kyle's been building bob weights here, so notice that the balancer only goes on in one direction. Here's the keyway. There's only one keyway. Has to put it on there. balance weight can only go in one spot. If it was backwards, it would be catastrophic. Flywheel is the same way. Notice the weight, it's right here. Now, the weight, because these are externally balanced, always is with the bob or the counterweight. So this counterweight is actually being added to here. Nate asked a good question, which was?
How do you know where to line it up if there's no dowel pin or something like that?
Because the bolt patterns are not symmetrical. They only go on one way. It forces the weight to be in their proper spot. So now, I would show you, but I physically cannot show you. You cannot spin this crankshaft much over 100 RPM without it bouncing so hard it'll throw itself out of the machine if you don't put the bob weights on it. I didn't tell you that before, did I, Nick?
No, I didn't know that before.
You know that, yes. You cannot spin this freaking crank. You know what crankshaft you would spin with no bob weight? If you can answer the question of what kind of crankshaft you spin with no bob weight and balance the crankshaft like that, I'll be impressed. So this is how this spins. So this has this variable rate motor down here that spins and drives the crankshaft. All right. So you see it down there, spinny, winny, winny. Now, what you want to do, there are different kinds of bob weights. This is a good, the all-around general bob weight that will fit everything. Universal. So what we want to do is we set this crankshaft up so the #1 journal is all the way up. We put these flat on there, and what we're doing is we're just trying to make sure that the bob weights are in the same position on each crankshaft. So we don't put this bob weight right here in the exact same way. We turn the crankshaft so it's up and so they're in the same orientation.
So that they're all 90 degrees from each other.
So they're all 90, thank you. So they're all 90 degrees from each other. Smart. Alec. Now, the way you check that is use the other side of the level. Right there's 90 and put that in level.
Level.
Level. Huh? Plum. Is that plum?
Plum.
Plum. Okay.
Up and down.
Plum. I like level. This part would be level. Then this part would be plum. Oh, all right. That makes sense. Like that. That's plum. That's level.
Okay.
All right. So here, Kyle's got all the bob weights on it. All right. You want to, now we have to put in a position encoder because this is not doing anything other than measuring the position of the crankshaft. So you turn the crankshaft, turns there. It is giving us a, oh, gotta hit that, Kyle. My touch screen doesn't work anymore. Randy, CWT. You can see here, I'm turning the crankshaft and it takes its position. Now, there's a bunch of little information you have to enter into the computer so it actually knows what crankshaft it is. So Kyle's already got all that set. So it needs to know how far this distance is from here to here. It needs to know where you're going to take the weight out at or add weight into it. And so there's some stuff that just really doesn't matter. It does matter, but doesn't really matter to you. So there's some settings we have to do in there. So here's the primary part is then we're going to spin this up. Now, as we spin this up, we're going to start this out slow. All right. Now here, we'll just put a little bit of lube on the bearings. That's a 100 RPM, 98 actually. That's 100 RPM. What 100 RPM looks like. Now let's get this thing up. It won't even measure until it gets to 500. Now that is 500 RPM. Now look at how fast that is whirling. That's not even idling and how fast that's going. So imagine how fast this is going, what's going on when you try to spin this up faster and faster and faster. I mean, it is scary. And these things, the bob weights and everything, are just hanging out there. It's scary. I would never do it. I don't even even when it's spinning 500 RPM, I don't stand where Nate is standing with the camera.
In the kill zone.
You're in, that's right, you're in the kill zone right there.
Cameraman never dies though. So.
As long as you don't drop the camera, we're okay.
Okay.
Don't drop the freaking camera. Okay. So now we just spun that up. Bada bing, bada boom. It is 54 grams out in the rear and 53 grams out in the front. All right. So we'll turn this to where it tells us to go. Super easy. Now, since it is super logical, all right, Kyle. So Kyle, super logical. Your connecting rod is lighter than your old one. So therefore, you would have to make the counterweight lighter. So if you took weight off here, you should have to take weight off here. It's directly opposite of it. So it's telling us to take 53 grams out right there. And in the back, it's telling us to take 54 grams out right there. All right. So all that is a matter of Kyle's going to drill a hole right here. Kyle's going to drill a hole right here. Basically, it gives us a rough idea of how deep a hole to drill, what diameter hole to drill, all that kind of stuff. And you kind of sneak up on it. You drill, you check it, you drill, you check it. Hopefully it's done. Okay. So now you can see this thing as it's spinning and checking. Now, I want to show you something that is really interesting and is going to make you double think about this whole deal. All right. So let me get my stuff around here while Kyle's doing a little bit of work. Alrighty, let me show you this, and then I have this other thing to show you. It's crazy. Connecting rod. Now, the first thing I'll show you is here is a piece of paper, right? That thing, this is almost 1 gram. 9/10 of a gram. All right, 9/10 of a gram. Think about this. Oil. Here, let me do it right here. You think there's oil flying around inside your engine? Now this is just on the connecting rod. Okay. Oil's always flying around in there. All right. Otherwise, it wouldn't work. Huh. 1.5 grams. Now, remember, there's 2 connecting rods in there. There's pistons in there. Let's say you spray, there's oil. Heck, some engines have oil squirters, right? Some LS stuff, European stuff, oil squirters. People put oil squirters in there to spray oil up in there. How much do you think it changes the weight? Okay. So how much as the engine takes off? Oh, how about RPM? Think there's more oil flying around at higher RPM? It changes. How about let go of the trans brake button, the car takes off, oil kind of flows to the back. Maybe the back has more oil on it than the front. Weird stuff. So why do we get so fanatical about balancing stuff to the 1/10 of a gram? Or even just less than a gram, or even a gram. We can't even really determine how much oil is on something. This is lightweight oil. What if the oil's cold? What if the oil's hot? There's all these things about how much that oil alone would weigh. Now, they put a little one oil number in here for you.
Use the mouse.
I gotta use the mouse, sorry. But what this oil number represents is oil right there is on the rotating side. They are literally trying to figure out how much oil is in the galley right there. Right there. that whole little area. That's what they're talking about, that oil passage. All right. So now, so all this stuff, I'm not saying not to do it. Still do a good job. But if somebody is hinging their whole life on they do the absolute perfect balance job, I'm telling you, you can't. There is no absolute number in here. Now, let me show, because here, how do you account for that? You can't account for that in the engine. You cannot, because the variable changes so dramatically. You can't change the balance weight while the engine's running. It is one balance number. So you're taking the best number that you can. All right. Now, I'm going to show you something that is totally crazy that most everybody doesn't know or understand. All right. Now, we know that that crankshaft is 50 grams out, 54 grams out in the back, 53 grams out in the front, right? Now, Kyle didn't know this yet. Most people don't know this. This is why I'm showing you these things. There's this balance reciprocating weight percentage. Now, this is all part of the calculation of a bob weight. 50% is the standard of the industry, period. That's just the OEM, AERA, whatever you want to say. That is just standard. Okay. Now, here's what's crazy. They will take, now remember, every crankshaft is basically the same. Every principle is the same. The piston cup engines balance the same way, basically. Industry Pro Stock, Pro Modified, Nitromethane, it doesn't matter what it is. Formula One, doesn't matter what it is. Basically, it's all the same thing, same principle. So here's the interesting thing. In a high RPM, constant high RPM engine, typically they will balance at 51%. Same crankshaft, same style crank. We could balance this crankshaft at 51% because it would run smoother at a high continuous RPM. Okay, so at 51%, which is a very common number, watch your bob weight number change. Goes from 1734 to 1752. All right, now they will go up to 52%. All right, so the same crankshaft, same engine will undoubtedly run the same, be fine, be perfectly okay, maybe even a little bit better at a higher RPM. But the standard is 50. You could change it and make it 51, and it's 20 some odd grams different. Now, if you go to a other type of engines that need to accelerate, typically they'll balance those at, so drag race style engines, something that's varying RPM, going down low, up, 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 like that, okay? Typically, they like to balance those at, now this is all general information on this part, okay? 49%. Some reason, I don't know why, doesn't matter to me. Some reason, 49% or even 48%, they think accelerates better and faster and has just a better acceleration characteristics. Still balances out fine. So at 49%, it's 1715. So now it's lighter. So the difference in between 49% and 51% being about 30 grams. Am I thinking about that right? 25, 35, 50, 40, about 40 grams. So this same crankshaft would have zero noticeable or zero practical, zero dynamic, zero any kind of thing you want to say effect in that whole 40 gram range. It's fine. So it would run perfect at 49% at 1715. It would run perfect at 1750. Does not care. It might just have a little better characteristic up here. Maybe it accelerates better. Maybe it has here. Anything's better. So the point of the whole thing is there is no absolute perfect way to balance. I'm just trying to help you understand how things actually work in the real world. We know you can't simulate what's going on in the crankcase for windage. It's a guess at best. We know that it will run perfectly well within this 40, and even if we did it at 2% on each side of it, it ends up being about 80 grams different. It's amazing. So within all practical reason, Kyle wouldn't even have to balance this crankshaft. We're still going to put it at the industry standard, still go through other things because there's no reason not to. But that is within spec of never even knowing it. You never feel it, you never see it. There was no problem with that balance being out of weight, period. Because we can simulate it right here. That would be 2% different than what it is right now. Maybe slightly over, okay? But we're gonna put it at that industry standard. Now, one last thing before we show this thing, there is one thing that really does matter, okay? Internal balancing is better. I'd like to have everything inside from the bearing, inside the bearing. That's why internal balance crankshafts are better. So it is always better to do an internal balance. But on a factory crank that is externally balanced, it is big money to throw Mallory metal in it to get it to internally balance. Simulating that weight right there is expensive. That's probably another $400 or $500 minimum to balance a crankshaft if we did that. Okay, but the real important thing is that you'll also notice that it wants 53 grams removed here in the front, right there, and almost exactly opposite, in fact 190-degree difference, it wants 54 grams removed. That is okay. As long as the two weights are opposite of each other, they counteract each other. That might not be the exact right term, analogy, but they counteract each other. Now, what is a big problem and what you can't do, which causes a big problem, is that if it wants, if you let it go and it wants 50 grams of material out right here and 50 grams of material out right here, where there's nothing, if the crankshaft was that way, what it does is it jumps rope. Then the two weights are on the same side, same plane. Whoop, 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 whoop. Goes like that. When they're opposite, like this, they're turning like this, and they counteract each other. Very interesting. All right, so that is how things are balanced. Showed you the whole balancing job. We'll show Kyle a drill here, and he's going to get it down to the industry standard, all right, of 50%. Just because it's a good general thing to do. I'm not saying don't balance crankshaft. I'm not saying don't do your due diligence. I'm just saying there is no absolute number. There's no absolute perfect. There's a lot of things that are like that. There is absolute works perfectly good, but there is no absolute perfect. Makes sense. Does that make sense?
You only had to say it 5 times.
I only said it 5 times. Yes, but I know. See, I'm just repeating myself. Yep. So anyways, Kyle's going to do the rest of this balance job. Leave your comments. Leave your questions. It's all cool. I'll still pick out my favorite one and send you a t-shirt or hat or something like that. Probably need to stop standing here so Kyle can do his work and get done and go home. Right?
That's right.
All right. So, I'm Steve Morris. Have a great day.